Our topic for the presentation is repeated padding for the sequential recommendation. I, Abhishek Gautam, Ayush, and Haribhajan will be presenting the paper presentation. Let's begin by discussing a key issue in the current state of sequential recommendation systems, traditional padding. In models, padding is applied to the sequence that are shorter than the predefined maximum length. Typically, the padding content is just zeros, which don't carry any meaningful information. This leads to the wasted input space, as zeros are ignored during the model's calculation. While padding ensures that all sequences are the same length, it does not contribute to the model's ability to make the better prediction. So what's our goal? Goal of our research is to improve sequential recommendation system by rethinking how padding is handled. Instead of using zeros, we wanted to explore whether the padding space can be better utilized, thus improving the model performance and training efficiency. So the paper proposes the solution as follows. To address this problem, we propose a novel approach called the repeated padding, in short named as RepPad. RepPad is a data augmentation method designed specifically for sequential recommendation tasks. In these tasks, the model's objective is to predict a user next likely interaction, such as what a product or service they might want to engage with next. A solution leverages the idle padding space by filling it with the meaningful data from the sequence itself, making the padding content more informative. RapPad is simple yet effective strategy that can significantly enhance the performance of the recommendation model without requiring any additional parameters of complex training process. Let's have the introduction to the sequential recommendation, which is the core of the many model recommendation systems. Sequential recommendation system aim to predict a user's next likely interaction based on their past behavior. These systems are built on the understanding that the user recent actions are most informative indicators of what they might do next. For example, in the e-commerce platform, if a user has been browsing laptops, the system might recommend accessories like laptop bags or headphones next. In streaming services like Netflix or Spotify, if a user has recently watched a series or listened to a specific genre, the system will recommend shows, movies, or music that align with the recent interest. The power of the sequential recommendation lies in the ability to personalize the user experience. Unlike genetic recommendation system that suggest item based on the broader pattern or static preferences, sequential recommendation system tailor suggests based on the recent and historical behavior patterns of each user. This makes the prediction more relevant, accurate, and engaging. So, as you can see, SR is the crucial in making recommendations that feel more intuitive and aligned with what the users truly wants, creating a more dynamic and satisfying experience. Let's move on to the next slide.
So coming to the problem statement, let's now address the core issue we identified with traditional zero padding method. As we discussed earlier, padding is used to ensure sequences are of uniform length of model input. However, the common practice has been to fill any extra space with value zero. The problem here is that zeros are placeholders. They don't provide any valuable information to the model. Essentially, these padding positions become dead space in the data. The model receives input data that includes real user interactions, but the padding sections don't contribute to the learning about the user's preference. Because these zero padded sections aren't used in models calculation, this means we are leaving a portion of model's capacity unused. We are not allowing the model to learn from every part of the input, which could limit its ability to make accurate predictions. The research question comes is with this issue in mind, we asked ourselves an important question. Can we make a padding work better for the model? Instead of simply using the zeros, can we fill the padding space with the relevant data and reflect on users' preference behavior? So the question led to the exploration of repeated padding RepPad. Rather than using zeros, RepPad proposes to fill the padding space with the user's actual past interactions. This way, even the padding sections of input contains valuable information. enhancing the model's ability to learn from the entire sequence and improving its overall performance. So the coming to the proposed solution. Now let's dive into the proposed solution, repeated padding. Basically, the core concept behind rep pad is simple yet effective. Rather than filling the padding spaces with zeros, we reuse the actual data from the user's past interactions. If a user's interaction history is shorter than required, instead of adding zeros, RepPad repeats the same sequence of interactions to fill the empty space. For example, if user has interacted with only 3 items, but the model requires a sequence of 5 items, RepPad would repeat those first 3 interactions to fill the remaining 2 positions. This ensures that every part of the input sequence contains meaningful data that reflects the user's preference. By reusing the valuable past interactions, RepPad can help the model learn better from the entire sequences rather than leaving parts of input unused. Coming to the mechanism, padding with repeats. The original sequence of interactions repeated multiple times until it reaches the maximum required length. So for a user with a shorter interaction history, the sequence will be padded by repeating their actual behavior rather than adding just the zeros. By using the delimiter, we prevent the model from treating the repeated sequence as one long continuous interaction and add delimiter, often the zero between each repeated sequence. This delimiter signals to the model that the repeated sequence are separate instances of interaction, ensuring the padding doesn't distort the relationships within the data. So, what is the advantage? So, one key advantage of RepPad is its simplicity and flexibility. Unlike other complex data augmentation techniques that require additional parameters or tuning, RepPad is a plug and play solution. It can seamlessly integrate into any sequential recommendation model, whether it's RNN, CNN, or transformer model, without needing modifications to the underlying architecture. RepPad provides a straightforward way to fully utilize the input space in a way that enhances model learning while keeping the implementation process clean and efficient. So, what's the setup for the experimentation? Looking at the experiment part, first of all, the data used. We used several data sets were used to evaluate the RepPad's performance across different user interactions, histories, and real-world scenarios. Toys, beauty, sports, Yelp, home. These data sets represent short sequence interactions where users have relatively brief interaction history. These are more reflective of real-world scenarios where most users have limited interaction data. Movie length. In contrast, this data contains long sequence interactions representing users with extensive history. It allowed us to test how RepPad performs when dealing with larger, more complex data with richer historical data. By testing on both short sequence and long sequence data set, the we were able to assess the RepPad's versatility and effectiveness in different settings. Evaluation matrix. To measure the RepPad, high ratio was used. This metric evaluates the accuracy of model by measuring the percentage of correct recommendation within the top key items. Essentially tells us how often the correct item appears in the model's top recommendation. Normalized discounted cumulative gain. This metric takes into account the rank of correct recommendations. It rewards models for placing correct recommendation higher in the rank list, giving more importance to higher ranked items. We tested both metrics with k values of 10, 5, and 20 to understand the model's effectiveness at various level of recommendation. So RepPad was tested on several types of models, including an RNN-based model, GRU. These models are designed to handle sequential data and capture temporal patterns in user behavior. A CNN-based model, these models focus on capturing local sequence patterns and identifying short-term dependencies. An MLP-based model, this is a simpler architecture that was included for comparison, helping us evaluate how RepPad performs even on basic models. A transformer-based model, these are designed to capture complex dependencies within the sequence using self-attention mechanism to better understand the relationship between different items. By testing and rapid on variety of model architecture, it was ensured that proposed solution was versatile and could be applied across range of sequential recommendation models.
Okay, so now let's take a look at the result from the experiments we conducted to evaluate RepPad's effectiveness. A RepPad showed a significant improvement in short sequence datasets. For example, on datasets like toys and beauty, where users tend to have shorter interaction histories, we saw performance gains of up to 60.3% on GRU4 REC model and 24.3% on SAS REC. These results demonstrate that RepPad is particularly effective when dealing with short user histories, which are quite common in real-world recommendation systems. In these cases, the padding space is more substantial, and by filling it with actual user interaction, we could maximize the model's learning capacity and improve its performance. However, RepPad wasn't as effective on datasets with longer sequences, such as movie lengths, where user histories are much more extensive. In these cases, there was already minimum unused padding space to begin with. As a result, the impact of RepPad was reduced and it didn't lead to significant improvements. This highlights an important limitation. RepPad is most beneficial when there's a substantial amount of unused padding space, which tends to occur when users have shorter interaction histories. On longer sequences, where the user history is already rich and complete, the need for padding is less and hence the method has a diminished impact. In summary, RepPad shows remarkable performance improvement for short sequences, but its impact is reduced when dealing with long sequences where padding plays a lesser role. This provides valuable insight into where and how RepPad can be most effective in real-world applications. Coming to the last slide, as we wrap up, let's summarize the key points and draw comparisons between RepPad and other data augmentation methods. In our experiment, RepPad consistently outperformed traditional heuristic method, while many data augmentation techniques rely on random or simple modification to the input data. RepPad introduces meaningful padding which provide a clear advantage. By reusing actual user interaction instead of padding with zeros, RepPad enhances the model's ability to learn and understand user preferences, making it a much more effective approach in sequential recommendation tasks. RepPad also stand out when compared to augmentation methods that require additional training. Unlike methods that introduce extra hyperparameters or require model training, RepPad doesn't require any training or tuning. It works out of the box as a plug-and-play solution, leading to comparable or superior results without added training costs. This makes RepPad not only effective but also efficient in real-world deployment. RepPad has shown impressive results, particularly on short sequence dataset, where it was able to boost performance up to 60.3%. By utilizing the available padding space more effectively, it ensures that even sections of the input that would otherwise be wasted are used to improve model performance. However, RepPad is less effective on long sequence datasets, such as those with extensive user histories. In these cases, the padding space is minimal, limiting the impact of the technique. This underscores the importance of considering sequence length when applying RepPad, as it works best in scenarios where padding space can be leveraged for additional learning. Looking ahead, there are opportunities to expand RepPad application to other data types and domains. To optimize its performance further, perhaps by adapting it to handle longer sequences more effectively or testing it with more complex model. will be an important direction for future research. So in conclusion, RepPad presents a novel and simple solution to improve the performance of sequential recommendation models, especially in cases involving histories, user interaction histories. Its ability to make better use of padding space sets it apart from traditional methods and offers a low-cost, high-reward approach to data augmentation in this field. Thank you for your attention.